So we are going to talk about 60 gigahertz. And 60 gigahertz is also known as millimeter waves. So we will talk about why it is good or bad, and then what the standards bodies are doing. So we are not just going to talk about LAN, but also other standards, ECMA, PAN, and wireless HDD. They all use 60 gigahertz. So 60 gigahertz is started, basically 60 gigahertz has been around forever, but FCC gave it for now I'm going to use the word unlicensed. The reason I'm going to use the word unlicensed is because yesterday I was reading the FCC document and they use unlicensed. So maybe these people in WiMAX forum were not so accurate, but this is the FCC document that August 2013. So last year they announced that we will make it available, right? But I think they announced it in August 2013, but probably 5 years before that people knew that this is going to happen. Okay? Or maybe they changed something in August, but they had something. So anyway, so the idea is very recently FCC announced that we will make available that band for license exempt use, and anybody can use it. Before that it was licensed spectrum, and actually WiMAX had used it for licensed spectrum, part of it. And so every country has a different band though. Reason every country has a different band is because they already had it allocated for something else, and it becomes very difficult to get rid of that equipment which is using it for something important. And so in America we have it from 57 to 64 gigahertz, in Japan 59 to 66, in EU 57 to 66, and so on and so forth. So you got 7 to 9 gigahertz total. 7 here, 9 there. And it's all in here. If you remember the electromagnetic spectrum, this falls, the 30 gigahertz is 10 millimeter and 300 gigahertz is 1 millimeter. You can do the wavelength to frequency translation. So this is between 1 and 10. That's why it is called millimeter waves. Okay? Light is here, infrared is there. Anyway, so now FCC doesn't put this into any kind of channelization. Basically, they give you the beginning and the end, and they give you some rules about how much power you can transmit and what you need to do. And then the standard bodies divide the spectrum or decide how to use the spectrum. So they put the channelization. So the main rule from FCC is that your EIRP should be 43 dBm. So now what is EIRP? EIRP is equivalent isotropically radiated power. So if you are going to do a directional transmission, generally you have the main direction, and then there is some side lobes, as we call them. Basically they just happen by the design of the antenna. So the main direction, there will be a lot of power going in the main direction and no power going in the other directions, right? And so if there was an isotropic antenna which did not have this characteristic, it was basically transmitting in all directions, and whatever power you get here, the power they would have sent would be called EIRP. So here the power that you are receiving is equivalent to if somebody would have sent 43 dBm all around. Okay? So now how can you get 43 dBm all around? You can just send 27 dBm from here, and then you can have an antenna that concentrates into one direction and thereby adding 16 dBm. So 27 plus 16 is 43. So the antenna gain is 16 dBi. Yeah, antenna gain is specified as dBi for that reason actually. dBi, I is for isotropic. Alright, every country has their own different transmit powers. Basically when you design the equipment, you take the minimum of everything so that you can sell the same equipment everywhere, right? And so that is what they will do. Same thing for the spectrum. Obviously, there is so much spectrum, but most equipment manufacturers will try to use one that is worldwide, right? And so you need to do that. Okay, all right. Any question about EIRP? Yeah. I'm sorry, what is it?
Why they are different?
What, different countries have different? Every country is independently owned and operated. You cannot tell some country that, see, please make it available here, Yeah, so that's the problem. Basically, they could make a UNO rule saying that every country has to do 10 dBm, done. But UNO doesn't make any rules that apply to all the countries, except human rights maybe, even those they cannot enforce. So there are no worldwide rules.
So the acceptability of radiation for health reasons, the benchmark is different in different countries. EIRP is quoted for on these devices for health reasons, that this is what human body can safely absorb. So some countries are more stringent, some are lesser stringent.
Okay, that is partly true, is that it is the health reason, but the power that is specified here, I would understand next to that antenna, 27 dBm. That's several watts of power, right? Like we said, milliwatt I wouldn't put next to my ear. So the thing is, there are two assumptions here. One is that how far you will stand from the antenna, right? And so when we had WiMAX, the power was even higher, because WiMAX antenna is on the top of a mountain, and for 1 mile you won't see a human being, right? Most of the range standards that we are talking about today is in your living room next to the TV, and you will be standing next to it, right? So the powers are low, and the powers for 82.11n were much lower, right? So there is give and take. Actually, the give is that the technology people want more, and the government wants to save people, just like he said, health reasons. But then will say, I cannot do anything with this, 1 watt of power, thing like that, right? So there is some give on the consumer side. So what is good about 60 gigahertz band? Why there is so much interest? 7 reasons. First, it's easy to get lot of spectrum. 7 gigahertz is lot of spectrum. You cannot ask 7 gigahertz when you are running at 2.4 gigahertz spectrum, right? There you ask in megahertz. Here you can ask in gigahertz, right? And with just 1 bit per hertz, you can get 7 gigabits. You don't have to worry about 64 QAM and 256 QAMs. BPSK will do. And so that is first thing, lot of spectrum. That is the best way to get lot of bandwidth, lot of data rate. Second thing is antenna separation. Remember I told you that the antenna separation is lambda by 4. For 2.4 gigahertz, the lambda was how much? 12 centimeters. So it was 3 centimeters required. Here, the lambda is 5 millimeter. So the separation is 1 millimeter, 1.25 millimeter. So you can put lots of antennas in a little chip. Okay? And so they generally make antenna array on the chip, and once you have these antennas, you can just put them in different phases and directions and things like that. Easily you can do beam farming. Low interference. And second thing is, because it is all directional. Actually, it is very close to the light in that sense. Remember, in the spectrum that you saw, the light was just, few power of tens away. But the thing is, light goes straight, radio waves can turn around, because they can turn around the objects which are close to their wavelength, right? And this is very small wavelength, and therefore this cannot go around anything. If you just put your hand, it is gone. That's it. And so it does not cross walls, and it is good for urban neighbors. If you are living in an apartment complex, you can enjoy your 60 gigahertz, and they can enjoy 60 gigahertz and not see each other. All right. Directional antennas. Since everything is directional, spatial reuse is easy. A can talk to B and C can talk to D and not worry about it. Yeah.
Since this is a directional antenna, would you use like relays or repeaters for?
Yeah. Yeah, we'll come to that in a minute. Yeah. Yeah, we do. Inherent security. Because nobody else can hear you unless they are right in the middle of you and your talker. They put their ear just next to your mouth. The thing is, so it is secure like that, right? And higher power transmission. FCC allows 27 dBm, but people cannot even find amplifiers at that power, so they use 10 dBm. Okay? And other countries allow 10 dBm for that reason, because they say if you cannot find an amplifier, why should we allow you that much? Alright, so let's see. At 60 gigahertz, you use 10 dBm and 30 dBi antenna to get that 43. At 11N, you put 22 dBm and 3 dBi antenna to get 25. So there we go almost up to the limit allowed, but we don't use antenna gain. Here we just use the antenna gain as the main thing. Antenna gain is easy. Directions are easy. Alright, when there is the other side of the coin, right? When there is an advantage, there are disadvantages. So the disadvantage is attenuation is proportional to frequency square. Does anybody remember what law was that called? Examination is next week. Next Monday is the first exam. So by now all the laws should be on your fingertips. But there was a law, FRII, Fry's law, whatever, that said that attenuation is proportional to frequency square. Higher the frequency, the more attenuation, the shorter distance you go. Okay, remember that. That is a fundamental law. Second thing, it so happens that at 60 gigahertz in particular, this somehow matches with the oxygen molecules structure, whatever that is, that if there is oxygen present, it won't go very far. And oxygen is present, of course. Otherwise, you won't be there. So, it doesn't go very far. Need high antenna gain, so you need directional antennas. That is actually, we said positive and now it's a negative here. And therefore, because of all this, you can go very short distance, not 10 meters is that what we go here. Okay, 10 meters. Now, at this point, you can start asking, can you have a local area networks in 10 meters? Should it not be called personal area network? And that's where the definitions get merged. Just like, there is no question, and I'm asking this is layer 1, 2, or 3, because all the layers are doing the same thing, retransmissions, routing, and so on and so forth. Similarly, there is no question asking whether it is a local area or personal area, whatever it is. Everybody is doing that. So, yeah, it is 10 meters. And there are two standards we'll discuss. One is called local area networks from IEEE, and there is another standard from IEEE, it's called personal area networks. Both do exactly the same thing, same distances. Okay? So the naming is just irrelevant now. And then if it is directional, there is a directional deafness. Basically, you cannot hear people who are not in the direction of your ears. So somebody is talking here, they might be interfering with you, but you don't hear it because they are not aligned to you. Right? And that creates new issues, is that carrier sense is, so this actually showing the deafness, this lady is going deaf, but basically the idea is carrier sense is not possible. So you cannot say, well, I will see if the medium is available. Medium is available, it depends upon the receiver. Right? If somebody is talking to the receiver, it is not available. If nobody is talking, it is available. So that is that RTS, CTS does not work. Multicast is difficult, and if you want to send to 15 people, you have to align the antenna 15 times. Easily blocked. And if you are watching a TV and suddenly the dog comes in, you're gone. The TV stops, and then you need a relay. That's what you talked about, relay. So what you need is something on the ceiling. You point to the ceiling and it goes there and comes down. And hopefully the dog will not jump. But the idea is that any little thing can block it. Okay? So you know the good and the bad. But the good is that it is being used. The products are there. I went to Amazon and found that, yeah, they are selling 60 gigahertz stuff. Right now you can buy it. It's arm and a leg. It costs a lot of money because nobody is buying it. So I mean, like, no, the thing is, that is a different issue, but it is there. So what can you do with it? First, cable replacement. Right now, if you look behind your TV, there is so much wire. Everybody's back of the TV is a mess, right? And so hopefully this will make it clean. Although I don't know. I mean, like, if with all that cleanliness, I want to put my hand there, but that is what it is supposed to be. Everything will talk to everything wirelessly. Your DVR, your computer, your camera will talk to the TV. And your storage, of course, yeah. And second thing is interactive gaming. So basically, you know, nowadays with what is the name of the Microsoft product? I forgot. Huh? Xbox? No, not Xbox. The Connect, yeah. With Connect, you know, you can have, they call interactive gaming. You know, you can play basketball, you know, whatever you want to play with yourself. And and the camera recognizes you, what you're doing. And so that is another application. High-speed file transfer. You want to send me a 1 gigabyte file, you know, point just your iPhone to my iPhone. And here we go. And obviously backhaul. This was the application for which WiMAX was being designed. So basically, if you wanted to go, you know, high speed between the poles in the city, you could use this. All right. And there are predictions that right now most of us are buying dual band. So previously it was single band 2.4 gigahertz, which kind of is ending now, 2014. Dual band is basically 11N is dual band, but as we go into AC, it becomes single band. So basically dual band is going to increase in volume, and then triple band is going to start from this year, actually from next year, they are saying. Triple band. So when you buy a device, it will say 2.4, 5.8 and 60. Okay, but this is a prediction. And as I said, the devices are already in the market. So standards. So there is a 11 AD. There is a ECMA 387. ECMA is European Computer Manufacturers Association. They actually started much earlier, 2009 first edition, 2010 second edition. Around the same time, IEEE started 3C, 15.3C, and then wireless HD came from the television people. The television people were in a hurry to get something to replace the cables, and so they already have the product, and that's where the products are. Most of the products are wireless HD products. Then there are other standards which actually I don't think they succeeded because I haven't seen much of them. WiMAX had a standard in 2001, 13 years ago, which allowed 10 to 66 gigahertz licensed band. Okay, so the carrier could go to the FCC, get a license, and then use that band. I don't think many people did. Japanese Arab is Association for Radio Industries and Business. They had it in 2005 millimeter wave radio for video and data, two standards. Actually, one of the numbers is wrong. Okay, so I mean, I will find the right number, but they cannot be the same number. So there are two standards, one is for video and one is for data. Okay, now having all these standards, I'm not going to talk about these last three, we're just going to talk about these first four. Now they are similar but different, and the purpose of talking about them is so that you know how different trade-offs are made in the design process of a network. Okay, everybody thinks differently, and so different decisions come back. 11AD. So 11AD is 2012, the last and latest standard. So hopefully this should be the best. Although once you study it, it looks like these are the same people who were doing 15.3c. So there is a lot of similarity between IEEE WPAN and IEEE WLAN. Okay, so first thing you define is the basic service set, and we call it personal basic service set, PBSS. So if you remember before, we had BSS, basic service set, a basic service area, BSA. Then we had extended service set, ESS. Now we have PBSS, which is personal basic service set. Basically, the group of stations which form one network. And PBSS control point or central point. So the central point PCP does the scheduling and timing. So now this is like a access point, but this is not called access point because you don't buy an access point. You just buy a TV and you buy a DVR, and they should be able to talk to each other. Right? And so one of them will become PCP. Alright? So any station should be able to do PCP. Not every station will be able to do PCP. So if you buy a little tiny thing, and I don't know which tiny thing, but basically if it doesn't have PCP, then it will not be able to talk. So at least when two people talk, one has to be PCP at least. Five people talk, obviously one has to be PCP. But in the example that I showed you a minute ago, there were two phones talking to each other at high speed. If the phones don't have PCP functionality, then they won't be able to talk. Okay, so this requires a PCP. And everything has a super frame. All the standards have super frame, and so in this case the super frame is called beacon interval. Basically this is a common thing on all wireless technologies that I have seen, is that basically you send out a beacon, well in most, let me put it this way, send out a beacon at a fixed interval, that is called super frame. We had it in 11AC, 11N, everything. So so beacon starts, and then the beacon will come next time after beacon interval. In this time frame, you have to have transmissions and announcements and everything else. So the first thing is beacon time. This is where now what we call PCP will announce, what is happening in the network. It will say, well, I am here, I am the PCP, my name is Boostal Encrypt, whatever, and now, then it will say, well, I have a frame for that person who was sleeping yesterday, and so sleeping frames, all those announcements will be in the beacon, right? And so that is the beacon time. The problem with the beacon time is that if I say it in this direction, these people will not hear. So I have to say it 15 times. This is a multicast. In every direction. So beacon time is there, and then associating beam forming time. Okay, by the way, you can read this in the next slide. I am not going to slide, I cannot turn two slides at the same time, but you can read at the same time on the next slide. Associating beam forming time is that after I say this, that I am here and I am the boss, I have to know everywhere where my people are. So I will talk to station 1, find out where they are. But that basically means align the antenna. So I will say to station 1, please, let's align our antennas. And so I will send them, how do you think now? What 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 do you think now? So we do this whole sweep, and you'll say, oh, your number 7 was the best. All right? And I said, okay, right, now let's go to 7. What do you think now? 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 So we do slight movement, right? Second phase we do very fine adjustment. He said, oh, your 7.3 was the best. That's how we find out the direction. In the process, he will also find out the direction. So we both find out what is the best direction for us to talk. That is called associating beam forming time. Now that we have associated, now I can say, okay, all right, you have 3 seconds, you have 5 seconds, you have 2 seconds, so we can have announcement time. Now I can make all the announcements. Okay? And then everybody knows what time they have. Then they can transfer it. SP is service period, which is basically pre-allocated. So I can say you can talk for 3 microseconds starting at that time and ending at that time. You can talk for 2 microseconds starting at that time. And then after that we have contention based period, CBP. So if you didn't tell me before and you need the time, you can go ahead and try it out. That is contention based period. That is where you do things like DFS, if anybody remembers what is DFS, and PCF. DSF was distributed coordination, DCF, distributed coordination function, and PCF was the point coordination function. Extensions of those were HCF for hybrid coordination function, and EDCF or something like that, enhanced distributed coordination function. Anyway, so all of those things are in the contention period. All right, so that is basically how we find each other. Now, let me see. I think I've covered everything in this slide. Yeah. So, I would change this word DTT to CBP because service period is pre-allocated. So, you don't need to use, you can use hybrid coordination function. Yeah, sorry, okay, so that's fine. DTT is fine. Basically, hybrid coordination function is pre-allocated, if you remember correctly, right? HCF was the pre-allocated part, and then DCF was the distributed coordination, was the contention part. So that's why you basically do those things in. So this is your HCF part, and this is your DCF part. Now the beacons, as I said, you have to send not just one beacon, you have to send many beacons in different antenna configurations. So when you have an antenna, you could have 3 antennas, but one antenna can move into 3 directions. So that is 3 sectors. So you have many antennas, and each antenna has many sectors. And so for every configuration, you have to just transmit to make sure that everybody hears it, right? So that's why here I have shown 4 beacons. This is 4 beacons are transmitted in this beacon interval, in this super frame. 4 beacons are transmitted in the second super frame, except that the starting point is rotated. So here the starting point was gray, here the starting point is blue, and the next starting point, is yellow. The next starting point will be blue, and so on. Antenna training, I think we have already talked about this, is that, and now this is not just between PCP and station X. Whenever station X wants to talk to station Y, they have to do antenna training. They have to find out what is the best antenna configuration. So A will send, many frames, we call them SS frames, to B, and B will send many frames to A, and they will find out what is the best configuration. Once they have done the sector level sweep, then they will do beam refinement, and beam refinement is that idea of, I know you are in sector 7, but let's find out where in sector 7 you are. Okay, so this is done in 2 phases. First phase, just the sector level. Second phase is inside the sector. This is shown much better here. So this particular, in this case actually both transmitter and receivers have 2 sectors, one here, right? So it sends out a very wide beam, and they figure out where they match, and then they will send out very fine beam in the sectors that they match. Is that clear now how all this works? So you find out. And by the way, there is a beam tracking as well. So beam tracking means that so you found out that okay, 7.5 is the best, and then you start transmitting in 7.5. In every frame, you will have something that will allow you to verify that yeah, you are reading it correctly. If you start getting 50% error rate or 25% error rate in that part, then you know that your beam has been interrupted or something went wrong. Right? That is called beam tracking. And then you will say, okay, all right, I think be time to realign. Okay, so there is beam search, there is beam tracking. So antenna training example, this is actually just a slightly another example than before. So in this case, the left antenna has 3 antennas. The left side has 3 antennas, and first antenna has 3 sectors, second antenna has 3 sectors, the third antenna has 2 sectors. So total 8 sectors. You see, it is possible to have 3 antennas and 8 sectors. Okay, so this has to try 8 different times. This one has only one antenna with 3 sectors. Sorry, 3 antenna with 1 sector each. 3 antennas with 1 sector each. So it has 3 sectors. Right? And so it's exactly the same process that I told you before. The only thing I wanted to point out and emphasize is that the number of sectors in an antenna are totally independent things. I mean, like you could have more sectors in one antenna and less in others. So now here what will you do is, you will really send 24 frames, 8 antennas, right? And there are 3, 8 times 3 is 24. You will send out 24 frames. It will hear into these 3 antennas and somehow then figure out what is the best antenna for itself and what is the best antenna for this. And then they will do second level if that is possible, right? So the first sector level sweep would be 24 frames like that. All right, so one thing should be clear by now is this whole thing about antenna training, which was not there before, because the things were not so directional.
What's the difference between this and the smart antenna used in N11N?
So beam forming is there, but I don't think in 11N they do beam aligning. Basically, the transmitter is the only one that is complex, which is access point, right? And it will just send in to you, and then will basically know where you are and send it to that direction. So you're right. So there is a beam forming there, which is same thing as directional aligning. However, this is actually in some senses bidirectional aligning, first of all. And second thing is, and this is the key to the operation. Whereas in 11N, it is just an improvement, a little improvement, few dBi extra, but was not really required.
So the biggest difference is there is no fixed core like the access point here. So,
well, actually, there is no access point, but that is a lie, because PCP is an access point. So in some sense, this is good and bad. Now, this is the kind of discussion that goes on in the standard bodies, is that now everybody has to pay the cost, whereas in access point, you just buy one access point and you have 100 dumb stations, and is that better than having 100 stations, 50 of them have to have an access point inside them, right? So there is a PCP which does everything that the access point would have done. Any other question? Now PCP cluster. So this is next level of complication, is that you will not have just one PBSS in a room. You might have more than one PBSS in the same room. So now they can interfere. We said that they don't generally interfere because things are directional, but Some people may not be part of your PBSS. I have my own PBSS in the same room. I have my computer, 2 computers, and maybe a screen. You have your computer, and so on and so forth, right? So you have your PBSS. So how do they coordinate? So then, you need a boss, and that boss is called SPCP, Synchronization PCP, who takes a bunch of PCPs and says, okay, all right, you guys, listen to me. And now, it will listen to all of them as well, and then say that, okay, so basically, so that nobody transmits at the same time as the other one. Actually, they all transmit at the same time. That's not a problem. They don't interfere. If I transmit in this direction and you transmit in the same direction, then we interfere. But if we transmit in different directions, there is no problem. In fact, that is one of the beauties of all of these 60 gigahertz is that the simultaneous transmission is allowed, which is not allowed in other standards before. So most of the time, people are talking in parallel without interfering. So SPCP is superbus, and it is called synchronization PCP, and the whole thing is called PCP cluster. So all PCPs select the beacon interval to be an integral multiple of that selected by SPCP. So that is one thing, is that suppose SPCP decided that my interval is 10 millisecond, then everybody has to select a multiple of 10 milliseconds. So I am going to send a beacon every 10 millisecond, and I am the SPCP. Then you could decide 20, you could decide 30, you could decide 40, you could decide 10. Any multiple of 10. And that is because now every 10 millisecond you will know the warnings. You will get, what you should not do or you should do. Right? And then you can pass on that to your members every 30 millisecond, 20 millisecond, or whatever number you have chosen. But you cannot do every 5 millisecond, because otherwise you will be you will have wrong information. So that's why it has to be multiple of what SPCP selects. All PCP allocate service periods in their schedule for BT. BT is the beacon time of all other PCPs. So they say, okay, all right. So now I'm going to allocate time, but since this person is transmitting at the same time, and so I cannot let you use that. So now this is like a big 2-level hierarchy here. All right, everybody knows what everybody is doing, and they avoid interfering with each other. All PCP here, all allocations, and avoid overlapping scheduling. That's all there is. A PCP cluster is a bigger set of stations, except that since one PCP cannot handle it, there are many PCPs, and then there is a boss PCP. Yeah.
Is the SPCP pre-selected or nominated?
Everything here is elected. So, if a DVR wants to talk to the TV, and both probably have the capacity to be PCP, so they will say, okay, I have capacity to be PCP, they will say, I will have capacity to PCP, and then at most they will have a priority built in, which will say, well, look, I have a higher priority because I have a 8-core CPU, whatever that is, and you have only 2-core CPU. So there is some priority, okay? And this is how it is done actually in other standards as well. In Ethernet, the way you select a route for a spanning tree is exactly the same way. Is that everybody has a capacity, but some people have priority. And you randomly select one with the lowest Ethernet address and the highest, lowest the priority number, which is actually highest priority. Okay? So same way here, they could just randomly select, okay, all right, what is your name, what is my name, or what is your address, what is my address. Okay, you have a lower address, go. You are the boss. It doesn't really matter. Okay? So yeah, PCP is not pre-assigned. PCP is elected when the station comes up. So basically when a station comes up, it listens for the beacons. If it doesn't find any beacons, it says, okay, I am the boss. I am going to start the beacon. It starts transmitting the beacons. And then if some second station comes on, it listens for the beacons and joins it. Spatial frequency sharing. So one thing should be clear, and I have already said many times, multiple transmissions may be scheduled on the same frequency at the same time if they don't interfere. All right? And VCP asks station to send results of directional channel quality during an overlapping SP. So if I ask you to transmit at the same time, U2 and U2, then I will ask, please send me the report as to what was the error rate. If the error rate is high, then I wouldn't do that next time. Right? If the error rate is low, I am happy, you are happy, we are all happy. Right? So that is what is done. The results of the, whenever overlapping SP, what is SP? SP is the service period. That is the pre-allocated time. All right? And the PCP then knows which station pair can share the same slot. Any question about this? Relays. So of course there are relays. So if the direct line of sight is blocked, LOS, then you have to go to somebody else and then they send it to you. The question is, what do they do? Do they send just the bit by bit or frame by frame? Just like in the days of Ethernet, there were two devices. Anybody remembers those two devices? In Ethernet, when you have multiple things connected to one device, central thing that was called switch is now, it was called hub before. In the hub days, you send bit by bit. Every bit you send went out in every direction. In the switch days, it doesn't send out every bit. It takes the whole frame and then sends it out. All right, much more efficient. But there is a delay, and there is circuitry required for storage, right? So hub doesn't have any storage. And so same thing here. They have two relays. One is called switch relay, and they could have called hub relays, but they call it cooperation relays. Switch relays, they operate like a switch. They receive complete frames from the source and then send it to the destination. These cooperation relays, they are like a hub. They amplify and forward, decode and forward every symbol. Now, here's the thing. It is possible that the destination may receive two signals, direct signal and relayed signal. And then it has to be smart enough to combine them so that it benefits, not interferes. So that brings us to the end of 802.11 AD. 7 things to remember now. Okay, and these are the 7 things that you should remember now. First is that the centralized scheduling. Only PCP can send beacons, and it sends beacons in all sectors. Second thing, there is a super frame which we call beacon interval in this case. It consists of beacon time, association time, announcement time, and the data transfer time. So there are 2 other functions other than beacon. There is a training and there is announcement. Announcement time is used for collecting requests, and data transfer can be pre-allocated or by contention. So that is why we have the data transfer time is in 2 parts. Antenna training is a 2-phase process. One is called sector selection, and other is called, actually not fine tuning, it is called beam search, I think. Let's see. Beam refinement. So there are 2 parts. One is sector level sweep and second is beam refinement. All right. Multiple transmission can take place on the same frequency, and that is called a spatial frequency sharing, and relays can be used if line of sight is blocked. Any question about 1180 before we go to the next standard? Is it all clear? By the way, in the process, actually, I probably passed through some references, and this is the reference. This book has this standard, September 2011. All right, we go to the next standard. ECMA 387. First completed in 2008 and second in 2012. So this is before IEEE 1180. And since there are two versions, the first edition and second edition, there is some confusion in the literature depending upon when it was written. And that's why it is really important that you read the latest books on this, because the latest is there are only two types of stations. The old one had three types of stations. Okay, so they have a high end and the low end, or high end and the middle end, or whatever standard. High end devices, they can do line of sight, non-line of sight, point to multi-point, and they can go up to 10 meters. So these are expensive devices, mostly TVs and DVRs. Economic devices are the standard devices which can do only line of sight, only point to point, and only go 3 meters. All right. So this could be your iPad or anything smaller than a TV. Type C was defined in the first edition but removed in the second edition. It took me quite a bit because I kept finding Type C, but I looked at the standard and couldn't find it. So then I looked at the two standards, first edition and the second edition. It was there in the first edition. Both the standards editions are available actually online. Right here is the reference for the second edition. I don't know whether you need to read that because standards are very difficult to read, but I put it here as a reference, not as a reading list. And two channels. So now they need two channels at the same time. One is called discovery channel to find each other and for antenna training. But if you're not doing one of those two things, you can use it as a data channel. But if somebody starts to do discovery, you have to get out. So there is a discovery channel, and then data channel is where you do the data exchange. All right. Now, this philosophy here is just the opposite of what is IEEE philosophy is. It is fully distributed MAC and there is no coordinator. So everybody has to work. And this debate about centralized versus distributed goes on every year for the last 40 years. Because there is no resolution to it. Distributed is good, centralized is good. Centralized is cheaper, generally more controllable. Distributed is more fault tolerant, but generally more expensive. Now everybody has to have PCP capability. Right? They don't call it PCP, by the way. But whatever is required, everybody has to be able to do that. All right, so how does it work? You have a super frame, and that interval is called discovery. The time of discovery channel consists of discovery intervals. So we call them DIs rather than beacon time, BTs. Each device performs a discovery block set during a DI. So every device tries to discover everybody else. See, right there. Distributed is good, but now everybody has to find out everybody. Okay? So if you are type A device, you send type A discovery frame, then you send type B discovery block. Actually, block is not a frame, it is you send a frame and you get the response scan, then you get the type A scan, and then you do the same thing in next sector, next sector, next sector, next sector. So basically, type A devices will do type A and type B, and type B devices will do type B and some type A, which is coming up in the next slide. So each device performs a discovery block set. This is called a DBS, discovery block set. This is a discovery block and this is a set. Alright, discovery block is simply finding out if there is somebody in this direction. So type A DBS. Type A DBS consists of sending a type A discovery frame, type B discovery frame, type B scanning, type A scanning, followed by lots of type B discovery frames in all other sectors. The first sector is incremented in successive scans. So what that means is, just like previously we saw, if you start in sector 1 and you did this extra work in sector 1, the next time you will do this in sector 2. Okay? The next time in sector 3. So type A will be heard in every sector, but only infrequently, where type B will be heard every single time. In successive scan, you rotate the first sector. Type A devices scan the channel and respond to DBS frames from other stations at the time indicated in the frames. So here is a type A discovery frame. It says, please let me know if you hear me. And so the answer comes back right here. Okay? So the time is indicated when you can tell me. Type A station may perform antenna training or start data transmission. So after all this is done, actually, after this is done, then if this is continues, after the discovery block set is done, then there is antenna training period. And type B DBS, now type B stations send the type B discovery frame and scan from the type B discovery responses, also respond to type B discovery frames of type A and type B stations. So type B will respond to this one, as well as if it was station of type B, then only these ones will be there. So whenever it hears type B, it just responds, period. Discovery channel can be used for data transmission, but discovery and antenna training have priority. If anybody wants to do antenna training or discovery, they have priority over data transmission. You could just decide that I want to transmit the data. But if somebody comes and says, oh, I want to do discovery, then they have priority. During each discovery, each station knows which neighbors are in each sector. So now the complete knowledge is at every place. Okay? A station sends an RTS on the discovery channel. RTS is ready to send, yeah. Discovery channel and waits it busy to one of its neighbor in a sector. So now I know you are in sector 7. I want to talk to you. I will say I am ready to send to you, and I'll obviously tell you how much time and to whom and all that, right? After receiving a CTS, the two stations exchange a series of tracking frames to determine the optimal antenna configuration. So after you say, okay, I'm clear to send, it means I'm ready to receive yours, then we align the antennas. Later, the station may perform antenna tracking, which we already talked about, to confirm the optimal operation by reserving some time during data transmission on the data channel. So this should all be clear by now, right? Basically, same way like before, we find the optimal configuration for transmission. We do the transmission, but while transmitting, we calculate the error rates. And if the error rates are too high, then we do something. Yeah.
Because there is the directional definition, why we still use the RTS and the CTS?
Yeah, right. The question is, we said that you don't use RTS, CTS in 60 gigahertz, and why are we using it here? So this basically is to make sure, now this is what is happening, is to make sure that you are not, see this is totally distributed. So it is quite possible that you are on the phone. When I try to call you, you are on the phone. Right? So I have to say, well, I mean, I have to give you a signal which says I want to talk. And then you say, okay, I am ready. So this is what it is that this is rather than general announcement, which was in 11N where everybody heard the RTS and CTS and stopped finding people. Here, this is not a general announcement. This is actually the term RTS, CTS is being used, but basically it is directed to a person. Directed to a station.
Model.
Huh?
Just we have a wire model. We still have RTS and the CTS.
We have the RTS and CTS. Yeah, right. But this is just to one person, as opposed to in 11N or before it was going to the whole world.
It's peer-to-peer.
Yeah, this is peer-to-peer. Good. All right, now the data channel. So super frame consists of the beacon period plus the data transfer period. Now each station sends a beacon during beacon period. Now this is another interesting part. Totally distributed. So in the other case, one PCP sent a beacon. Here we are sending, if there are 15 stations, there are 15 beacons. Everybody is sending a beacon. Alright? And in the beacon period, you find your slot when you can talk. So basically, you see if there is nobody else talking, then you know that you are the first one. You start a super frame and you take the first slot. But if there is already something going on, then you find the empty slot, or you find a slot where you can put yourself. So that's how you join. You just join a crowd. Okay? You go there and you see how many people in the crowd and where can you stand. And so this is totally distributed, right? So totally distributed means everybody sends a beacon. And stations listen during one subframe and find an empty slot for itself, find another if collision. So now if I went there and I found slot number 7 is available, and you went there at the same time and found slot number 7 is available, you collide. Next time, maybe you don't select 7, maybe we select different slot and hopefully will not collide. So there is a whole collision resolution mechanism. So basically, you see the thing is there are several beacons. Now what do you do in the beacons? In the beacons, you also announce that, look, I am here, I am station number 7, I want to talk to station number 9, please, for 3 milliseconds. So beacon has your request. Right? Now, if the station has heard it, then it will send its own beacon and say, well, I am ready to talk to you, station 7, and for 2 milliseconds, but not maybe 3 milliseconds, whatever, right? So this is how they negotiate. And then when they get the time, and actually it turns out they also negotiate when we will start. And I am not sure as to how you really find a time. So you listen to all these beacons, and then distributedly you just sit down and figure out everybody's requirement. Everybody figures out everybody's requirement and finds their own time. Okay? With PCP, obviously there's an algorithm which is similar to what PCP would have done. Here everybody is doing that. Okay? So you say, all right, we will start at 9 o'clock and talk for 15 minutes. So then they start. This is the cooperative transmission. Now, this is a complication which I was kind of surprised, but I have got to pass it on to you. Type B stations cannot receive type A beacons, but they can send a type A beacon. And then there is a whole paragraph as to why it is easier to send than to receive. They send both type A and type E beacons. Type B range is only 3 meters away and may not receive all type A beacons, which is 10 meters. Now, this is a little bit contradictory to what was said. Now it could be addition business, first addition versus second addition, I don't know. But this one says that type B can send both type A and type B. And here we had said that the type A can send both type A and type B, and type B sends only type B. So there is a slight contradiction among different books. Again, of course, I could go and check that standard, but it's such pain to read through. Let's see how many pages is that. 302 pages of this, and first edition is 302 pages of standards. That's not also, it's not written for reading. The standards are written for exactness, correctness, so that nobody can interpret it differently. And so they will use the word like shall, thing which we don't use in normal English, all the time. But, you shall implement or use, rather than use should, no. There's no should, shall. And so everything is prescriptive, right? So they're not very rigid. Anyway, so let's see. I was on this slide. No. Type B stations send to A and B, right? They can send. Beacon consists of source announcement of the required time, duration, antenna. This all we said already. That beacon, contains everything that I want to do. Destination checks their schedule and sends confirmations in their beacons. Everybody listens to everybody else request and check if there will be interference. So all of this is done distributed fashion basically. And the relays, type A devices that amplify and forward. So the relays are there too, which are type A devices. If direct transmission is blocked, relays can be reserved by a source destination pair by request and antenna training. So if I find that I cannot talk to B and I want to talk to B, then I would say, can you act as a relay? And relays will probably announce in their beacon that I am a relay. And so that's how it is done.
If we go by the first one,
yeah,
then type A devices cannot initiate communication with type B, whereas type B can initiate with both.
If I go by the first one,
it says B cannot receive, so A can keep on sending, B does not receive A beacons, so B cannot respond. Therefore, type A devices would not be able to start communication with B.
right. So here I think if I haven't given enough thought here. See, the thing is, if there are two kinds of people, one speaks English, one speaks Chinese, the communication is possible only if there is one person which speaks both. Right? Or in this case, everybody is everybody, right? So here's the thing, there is no one person here. So let's say, if we have two kinds of people, one speaks Chinese, one set of people speak Chinese, one speaks English, now how do we communicate? Chinese people have to speak English, and English people have to speak Chinese, or at least some subset of it. Right? And that's what it is here.
Or if we had TCP, we could have solved this.
Yeah, we could have solved the problem, yeah. It could have spoken both, right? Here, everybody has to speak both, in some sense, to tell everybody else that, look, I am doing this. All right, that actually brings us a good point in this lecture. We can compare the two philosophies. This is centralized philosophy, this is distributed philosophy between the AD and this 387. PCP is a single point of failure. This is always the thing about the centralized. Anytime you centralize, people will tell you that this is a single point of failure. And second thing is the PCP cannot sleep. If you turn off your TV, your DVR cannot talk, or whoever was, not a PCP cannot talk. So that is a problem. No single point of failure. One beacon is per sector. Here, omnidirectional beacons per device. So basically, that one is again little bit of contradiction. Here we see beacons per sector. So this is the omnidirectional beacon. So here what I said, when I was reading about ECMA 387, different books said different things, and I think this is what probably happened here. I'm not really sure whether this is true. Omnidirectional beacon per device. TCP antenna training with all the devices, only communicating pairs train antennas. So only when you talk to neighbor, you train the antenna. No dedicated control channel, dedicated discovery channel. Point to multi-point is easy. Here, all active correspondence written discovery channel periodically for antenna training, and therefore multicast is difficult. Basically, as I said, the type B stations are only point to point. So if you want to do multi-point, so then it is difficult, multicast. Ideal for data and multicast applications. So this is designed by IEEE for data. This is designed by ECMA for video. Video is point to point, data is point to multi-point. Okay.